Welcome to this explainer. Today we're taking those highly mathematical computer science concepts and translating them into practical, everyday coding terms. Have you ever written code that runs absolutely perfectly with 10 items, but then literally freezes your entire machine when you hit 10,000? Well, that is the invisible wall of algorithmic complexity. Today, we're going to break that wall down. We're taking the complex math of performance and efficiency and grounding it in easy-to-grasp concepts. To help us out, we'll be referencing the Algorithms Notes for Professionals book. It's this incredibly comprehensive 200-plus page guide compiled directly from Stack Overflow documentation. It is packed with a collective knowledge of thousands of developers, so it's really the perfect foundation to demystify all that intimidating programming jargon.
Okay, here's our roadmap for this journey. Number 1, welcome to algorithms. Number 2, the fizz-buzz test. Number 3, measuring algorithm complexity. Number 4, big O, theta, and omega. And finally, number 5, scaling up with loops and logs.
Let's dive right into Section 1. Welcome to algorithms, defining the problem.
As developers, we build algorithms every single day, right? But formally speaking, an algorithm is a set of precise instructions mapped to a very specific problem space. Take the problem of sorting, for example. You require a defined input. Maybe that's an array of strings like Haskell and Emacs, or just a random sequence of numbers. The algorithm's job is to guarantee a specific output, like perfectly ordering them from smallest to largest. If you change the input or output rules, well, you need a completely different algorithm.
Moving right along to Section 2, the fizz-buzz test, a practical anchor.
If you've ever sat through a software engineering interview, you absolutely know the classic fizz-buzz test. You iterate through a sequence of numbers. Multiples of 3 are fizz, multiples of 5 are buzz, and multiples of both are fizz-buzz. It sounds incredibly simple, kind of like a kid's game, but it actually forces a machine to make sequential, logical decisions.
When you write out the basic Swift code to solve this, it brilliantly illustrates the concept. We use standard if-else conditions and modulo operators to determine divisibility without a remainder. The code is basically running a sequential checklist. Divisible by 3 and 5? No? Okay, how about just 3? No? Just 5? It locates those fizzes and buzzes one by one, completely sequentially.
But wait, what happens when the input gets massive? Say scanning numbers from 1 to 100,000. In that sequential approach, checking if a number is divisible by 3 and 5 means the computer literally does the math twice. We can optimize this by checking for divisibility by 15 first. Since 15 is the lowest common multiple of 3 and 5, checking it once instantly prevents the computer from running redundant operations. This right here is the very beginning of thinking about algorithmic efficiency.
Which brings us to Section 3, measuring algorithm complexity and escaping those limits.
Think about the sheer explosion of work a computer has to do based purely on how an algorithm is designed. Constant time takes exactly one operation no matter what. Linear means 100 items takes 100 operations. But check out how drastically a quadratic algorithm scales. If you have just 100 items, a quadratic algorithm jumps to 10,000 operations instantly. If you had 1,000 items, that's 1,000,000 operations. This is exactly why poorly optimized code crashes systems.
So, let's get into Section 4, big O, theta, and omega. These are our mathematical tools.
To evaluate scale properly, we use asymptotic notations, starting with the most famous one, big O. Big O represents your worst-case scenario. Think of it as an absolute ceiling, calculating the upper limit of operations. It guarantees that no matter how messy or incredibly vast your data gets, your algorithm's running time will never exceed this trajectory. Basically, it answers the question, what is the absolute longest this could possibly take?
On the flip side, we have big omega, which acts as an asymptotic lower bound. It is the floor. This means that in the absolute best-case scenario, the algorithm will definitely take at least this much time, or this many operations to run. It's physically impossible for it to run any faster than this baseline.
And then there's big theta. This is the holy grail of precision. Big theta is a tight bound that essentially sandwiches your algorithm's performance right between an upper and a lower limit that grow at the exact same rate. If an algorithm is big theta of n, it means the speed of your code scales in direct, lockstep proportion with those bounds, no matter how huge the input gets.
The crucial takeaway here is that big theta sits squarely in the intersection of these concepts, kind of like the middle of a Venn diagram. It applies strictly and only when an algorithm is simultaneously big O, meaning it has that confirmed upper bound, and big omega, meaning it has that lower bound. If it satisfies both, it earns that incredibly precise classification of big theta.
Let's wrap things up with Section 5, scaling up with loops and logs. Say you write a simple, single loop to find the maximum value in an array. It just steps through the data once, right? That scales linearly. It's O of n. But let's say you want to find duplicate values. You might write a nested loop, a loop inside a loop. This means for every single item, you iterate through every other item in the entire list. That innocent-looking nested loop, yeah, it drops us right into that heavy, system-crashing O of n squared class. You basically go from a brisk walk to carrying a boulder up a mountain.
So n squared is terrible, and linear time is okay, but how do we actually beat linear time completely? Well, sometimes knowing the mathematical limit isn't enough. We don't just want to measure operations. We want to actively manipulate and reduce the problem space itself. Welcome to the absolute magic of O log n algorithms.
In O log n algorithms, like the classic binary search, the code doesn't just read data one by one. It looks at the middle of a sorted list, decides which half holds the answer, and literally throws the other half away. It fundamentally halves the problem size at every single step. N over 2, then N over 4, then N over 8.
Because of this continuous halving, the efficiency gains are staggering. To put that into perspective, searching a data set of 256 items linearly takes up to 256 checks. But logarithmically, by cutting the data in half each time, from 256 to 128 to 64 to 32 and so on, it guarantees a solution in a maximum of just 8 steps. That is the real tangible power of understanding algorithmic complexity.
So let me leave you with this final thought for your own coding practice. Imagine a massive, sorted list containing hundreds of thousands of negative and positive integers. If you need to find the exact index of the number 0, are you going to write code that checks every number one by one, or are you ready to have your problem space and find exactly what you need in record time?